In this video, we are going to discuss example 33 and improper integrations involving the integrand of 1 over 1 minus x. To proceed with the integrations, we first display the graph of the integrand function 1 over 1 minus x on a graph. The behavior of the function is such that when x is 0, the function takes on the value of 1, and the function will tend towards infinity when x tends towards the vertical asymptote of x equals to 1 from the left. The integrations to be performed involve limits of 0 and 1. This improper integration represents the area under the curve of the function that is bounded between the lower limit of 0 and the upper limit of 1, where the upper limit itself is an vertical asymptote. If you choose a value of b that is smaller than 1 but larger than 0, and you let the values of b to tend towards the asymptote 1 from the left, the functions will go to infinity as indicated. In the language of mathematics, this is represented by saying the limit of b tends towards 1 from the left for the function f is positive infinity. This is an improper integral of the second type because the functions encounter an infinity at one of the limits, which is x equals to 1. The area under the curve being considered is bounded between 0 and 1, where the function tends towards infinity when x tends towards 1. Will the area represented by this improper integral finite or infinite? As a comparison, we have seen in example 32, where we were considering an improper integration to obtain the area of this function 1 over square root of x bounded between 0 and 1. In this improper integration, the function is also tends towards infinity when x tends towards the vertical asymptote from the right towards x equals to 0. Despite that the function tends towards infinity, the area under the curve being considered turns out to be finite. So, a function that is diverging at one of the limits does not necessarily mean the area under the curve must be infinite. In this case, it shows that it is possible to obtain an finite area even though the function turns out to be not well defined in one of the limits. To proceed with our improper integration, like in the previous example, we will first replace the upper limit 1 by an finite values of b which is less than 1. By doing so, we would be able to avoid evaluating the integrand function at exactly the values of x equals to 1. So we will first proceed by replacing the improper integral by a proper one, where the upper limit of 1 is replaced by b. And b is defined to be a number which will always be less than 1 but never be exactly at 1. This turns out to be simply equals to a functions ln 1 minus b minus ln of 1, where ln 1 is simply the log of 1 minus x with x replaced by 0. And we know the log of 1 is 0, so that is simply equals to log of 1 minus b. Once we have obtained the expressions of the proper integral in terms of b, then the improper integration from 0 to 1 could then be expressed as the limit of the proper integral 1 minus x from 0 to b, with b tends towards 1 from the left. In the previous line, we have already shown the expressions of this proper integral is log of 1 minus b. Now, we need to evaluate the limit of log of 1 minus b when b tends towards 1 from the left. So let me represent the values of x equals to 1 on the x-axis and the values of b, which is always less than 1. Since b is always less than 1, therefore we define epsilon value, which is the difference between x equals to 1 and the values of b, so that the epsilon is always a positive number. In terms of epsilon, the same limit is written as log of epsilon, with epsilon goes towards 0. The log of epsilon is negative infinity in the limit where the epsilon is becoming increasingly small. Therefore, this would be just minus infinity. So we come back to this limit. Now I'm sorry, here I have missed a factor of minus because the integrations of 1 over 1 minus x evaluated between b and 0 has an minus sign. This minus sign is coming from the factor of minus 1 of the 1 minus x term. So there's a minus sign here for log of 1 minus b. Therefore, the limit of minus log of 1 minus b, according to our explanation here, would then give you a minus of minus infinity, which is positive infinity. As such, the improper integral is divergent. This is because the limit of the function 1 minus b is divergent when b tends towards 1 from the left. As a conclusion to this video, we have discussed the improper integral of 1 over 1 minus x with limits of 0 and 1. The first steps of performing this integration is to replace the upper limit of x equals to 1 by a value of b which is less than 1, so that the integrals from 0 to b is obtained in terms of log of 1 minus b with a minus sign. In the second step, we take the limit of b going to minus 1 for the expressions of this integral in terms of b. We have shown that the limit of the integral is divergent to positive infinity. This shows that the integrations between 0 and 1 is divergent. Therefore, it does not converge.